Hello guys, this is Farhan from AlgosFromScratch and I welcome all of you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. This is going to be the 6th video of this playlist, and in this specific video we are going to discuss about the embedding layer. So we will be building our embedding layer from scratch using PyTorch. So this is the layer that we are going to start with. So first of all, uh, we will build this complete embedding layer, and inside this embedding layer, if you notice, we have these positional embeddings, and then this token embeddings, layer normalization and dropout, and this is going to be the output. So let's say if we have two sentences, so we will have two, and this maximum length I mentioned previously as well. It is your choice. Either you can fix it to 128 or whatever you want. So if let's say your data has the maximum length for each example around 100, so then 128 I guess is the best option for you. By default its size is 512. The DistilBERT model gives us 512, and then this is the channel. Okay, so let's say if we pass two sentences to this embedding layer, and we will be getting this shape of output from this embedding layer, and then this shape we will be passing to the next layer. Okay, so starting with the embedding layer, so quickly just moving to this screen. Okay, this is again the same notebook. Okay, so let me just print the model. Okay, and if you look into this, this is the part that we are going to create. Okay, this embedding class. So let me just copy this, and I can just have another text. Let me just save it, and okay, here. Now I'll first of all start with the importing. Import torch.nn as nn. So we will be using this nn module from torch, PyTorch. So all of the layers, etc., we are going to implement from this. Then we are going to start with the class. Okay, so you can see we have this embeddings class. So we will be having the same class, and this class I am going to inherit from nn module. Now here I will be having my constructor, and this constructor will be getting, first of all, the vocab size. This vocab size is going to be, okay, so let me maintain this model config. It is going to be a dictionary, and here we will be having the vocab size is equal to 30522. Then we are going to have this same, let's say, model config. Let me execute this. Okay, what's the issue? This is the issue. Okay, so oops, my bad. So I am going to assign this config, and inside this config, this vocab, I am going to assign this config size, and okay, to this. Then the next thing that we going to need is, this is the dimension size. Okay, so I will just add another key value pair here, and that is going to be the dimension. And dimension, I will just be having 768. The model basically gives us this dimension for each token. So here I will be having dim, that is equal to model.config, and it will basically be taking this value of dimension from the model config. The next thing that we are going to need is, if you look into this, we also need this maximum length. Okay, so the maximum length is, I am going to add another key value pair here, and that is going to be the max length, max sequence length, to make it more clear, max sequence length. Okay, and this max sequence length is going to be, let's say, the similar one that model gives us by default. Okay, and here I will call it max length, and I am going to get it from the model config, and here I will just be using this, and yeah, like this. And next, what we also need to have this dropout, so let me add this dropout, and let me call it dropout embedding, and it is going to be 0.1. Okay, so I can do something here like maybe p equal to model config, and here I will be just calling this dropout embedding. Okay, so just to be on the safe side, let me copy and paste it. Oops, control C. Yep, let me just enter it. So okay, this is, I guess, pretty much it. Now let's just call our super, and here I'll start with the word embeddings first of all. Okay, so the first layer that I am going to create is self dot this word embeddings. Let me just copy paste it like this, and it will be equal to nn dot embedding, and here I will have the vocabulary size and the dimension. Okay, so here basically I am going to create a lookup table. Okay, and that lookup table is basically the lookup table for the token embeddings. It will be from 0 to 30521, and the dimension will be from 0 to 767, so it is 30522 768. This is going to be the size, and if you look into this, this is the same size. Okay, the second thing that I am going to do is, let me just copy this and paste it. Okay, here instead of the word embedding, now I am going to create this position embedding. Okay, and this position encoding is going to be equal to the max length times dimension. And next I am going to add a layer norm of dimension size. So layer norm is equal to nn dot layer norm, and it will be the dimension. Okay, then I am going to create the last constructor level argument, and that is dropout. So dropout is going to be equal to n_dropout, and this is like p, so we want to have around 10%. This is the value, okay, 0.1, so 10% of the weights we want to switch them off. Okay, now quickly, just if I come here and create an object, and that object is going to be the embedding class object. Okay, and let me just call it, okay, this is the issue. Okay, so I think we did not execute this after modifying this. If now, okay, model config, model config, where is basically this issue. Okay, so we have this model. Okay, yeah, it's working now. And if I just print the object, you can see this is the same class now. Embeddings, where we have word embeddings, it is 30, this one. Okay, so it is now similar to this one, you can see. Okay, this we can pass, okay, to the model over here, and it's nothing but we are asking PyTorch to treat these padding tokens with this ID. Okay, so padding ID is equal to 0. So yeah, that is all. I guess nothing else. I think I need to cut it from this text box, and it will be better if I just paste it in the coding block. Yeah, so this is the size. Okay, and let me just paste it right here. You can see embeddings, word embeddings, then embedding everything. You can see the same. Now if I just print it, yeah, padding IDs. Okay, this is by default true. Okay, so same going here and this one. Okay, so by default values with this, okay, I have this one, so I can just set this value over here in the layer norm. That is how you just execute it and check it. Okay, so yep, that is pretty much it, I guess. The in place equal to false, 0.1, this same. Now everything is good. Yep, now we just quickly need to add our forward function. Okay, so forward function is going to get the input IDs. Okay, and what we do with these input IDs, first of all, let me just extract the maybe batch size and also the dimension, no, sequence length, and we can get this with input IDs dot shape. Okay, once we do this, we can then pass the input embeddings input IDs to this self.word embedding to calculate our input embeddings. So we'll be getting the input embeddings against each token. Okay, so this is what we are going to do here. I will simply pass it to the self.word underscore embeddings. Okay, yeah, this is the right suggestion. I'm just passing it. Okay, and with this, simply, I guess that is pretty much it for this. So if I return this input embeddings now, and let me test this, okay, and I'll be testing it with, let me just copy some code from for this. Okay, so let me just copy this and I'll just paste it over here. Just one thing here, I think return tensors equal to, I just need to have pt. Okay, and if I just execute it and I just show you this out, and let's check its type. Okay, it is the okay, and let me just check the what's inside this, and let me just print it. Yeah, so it has input IDs, attention mask, each and everything. I just for now need the input IDs. I can print these input IDs. This is a tensor, you can see. Okay, and if I check it shape, it must be 1 by 128. Yes, so this I can simply now pass to the, I'll copy this. Okay, and here I'll just call object, and here I'll pass these input IDs. Okay, and input IDs is going to be equal to this out inputs. Okay, so let me remove this, execute this. Okay, so it says got an argument input IDs, and input IDs. Okay, so what's wrong? Let me check this. Okay, so it says unimplemented this forward got keyword argument input IDs. Let me first of all extract them just to make an extra layer, nothing else. Input IDs equal to this, and let me check what input IDs have. So input ID is equal to this. Yep, we have this. Now what's basically wrong if I simply just pass these? Okay, in missing required forward function. I think what could be the issue? Okay, and okay, so I was doing this mistake. I still am doing this mistake. I am not basically making any object of this class. Okay, nothing else. So it happens while doing this. Okay, no worries. And input IDs dot shape. No, basically I don't want this. I just want to call this shape. Okay, so in return I am basically getting 128 768. So these are the input embeddings. Now quickly I will be calculating these position embeddings. Okay, and these position embeddings are basically, if I just want to create the position embeddings, so I can calculate them like, let's say I have one by 128. This is my input size, And if I want to have these position embeddings for all of these, so I need to have this same shape. Okay, so I can then like broadcast it over the batch size, and I can calculate the position embeddings for all of the sequences. Okay, so let's say if we have 3 by 128, so we need to have the same size of position embeddings for all these positions. Okay, against all these these input sentences or values. Okay, so here, first of all, let me just create the torch dot arrange. Okay, and in this torch dot arrange, I am going to first of all pass this sequence length. So I will have to create first of all the first sequence. Okay, so if I do this, and along with this I will be having the t type equal to torch dot long. Okay, and also I will be putting it on the same device, okay, on which I basically have this input IDs. So the PyTorch can calculate or compute this later on to sum them on the same device. Otherwise the PyTorch is going to give us the error. Okay, so this, and if I just return this position IDs as well, and over here if I receive the, okay, here I will receive the input embeddings and also the position IDs equal to this, and simply I'll be doing this. And if I just now do this, and over here simply call this touch is not diff, okay, where I'm okay basically doing this, and yeah, so right now I think it should work. And yep, now if I just print the position IDs, you can see I have this position IDs tensor, and if I calculate its shape, you can see it is 128. So I have 128 position IDs for this one sequence. Now the next thing I want to do is I want to expand it on the batches. Okay, so for each batch I have the same position IDs. So position IDs is going to be then position IDs dot unsqueeze unsqueeze. Okay, and this unsqueeze 0 dot I will also expand it. Okay, and I'm going to expand it on the batch size. So whatever batch size I have, let's say this is our batch size, and also the sequence. Okay, like this. So now this position is okay. First of all, let me tell you what these what these two methods will be doing. So unsqueeze is at 0, it is going to add the dimension along the first position. Like let's say if now we have this shape of our position IDs, so with unsqueeze it will convert it to this. Yep, this one. Okay, so and okay, and then with this, now when we call the expand, okay, so this expand will basically convert its view basically this is very important point to remember. This expand function is not, this method is not going to create physical memories. Okay, the underlying memory will be the same. It will just be creating a view. Okay, and it is going to be then the batch size sequence. So for our, in this one sentence, we will have the same one by 128, but if we have, let's say, 3 sentences, then it becomes 3 1 to 8. Okay, and when we pass it to the position embedding layer, I will be doing right here, position embeddings equal to, I will be doing it like self dot position embeddings, and here I will be passing the position IDs. Okay, this. So if I now pass this, and let me just copy this and paste it over here, and over here I will receive them like this. Okay, so let me just execute this, and now if I just call this and EMB, okay, and let me check the shape. Okay, so I have now the same shape. Okay, so now I have the same shape for position and token embeddings. So I have 1 1 to 8 7 6 8 for input embeddings, and I also have the position embeddings like 1 128 7 6 8, so having the same shape. Okay, now I can perform this element wise addition. Okay, and this will give me the overall context. Like after this step, our input now knows 2 questions, like what I am and where I am in the sentence. Okay, so each and every token I will be performing this addition for. Okay, so after this, once we have this, let's say, we can calculate the embeddings, and these embeddings are going to be equal to the input embeddings. Okay, this input embeddings, and now this final position embeddings. Okay, and I'll just paste them. Okay, and instead of now these position embeddings, I'm not returning them now. I'm just returning the embeddings. Okay, and now if I come here and here, input embeddings, now input embeddings now have this shape of 1 128 768. Now this shape is a position aware, so it knows where each token is in the sentence. So this is the combination of input embeddings plus the position embeddings. Okay, and okay, so after this step now, okay, so these are these 2 first steps that I have executed. Okay, and now the next step is I am going to pass it through this layer normalization. So what this layer normalization will be doing to the input, it will basically normalize it. Okay, so I'm not going to dive deep into the layer normalization. That is a whole separate topic. I can have a dedicated video on this, but there's, you can say, 4 steps, or majorly 3 steps, you can say, that layer normalization will be doing. So first of all, it will be calculating its mean on each token, a vector. Okay, and it will be calculating the mean and variance. Okay, and then it will be normalizing it, okay, with the help of these 2 they have their own formulas. I again am not going to discuss them. Okay, and then finally it is going to apply the, let's say this is our y, so maybe something like y gamma plus beta, something like this. Okay, so these gamma and beta terms, they are learnable parameters in the layer normalization. Okay, and we can see them, we can in the model state dict, that in layer norm we have layer norm weights and layer norm bias, and this basically the gamma is weights. Okay, and this is the bias. So they basically are used to scale and shift. Okay, so this we are going to discuss in a separate video. Okay, but for this video I think this is pretty much enough. Okay, and okay, so now I am going to pass the same embeddings. Okay, from, so embeddings now is going to be equal to self dot layer norm, and here I will pass simply the embeddings. Okay, and these embeddings are now normalized embeddings. Okay, and finally I am going to pass it through the self dot dropout. Okay, and here I'll be passing the same embeddings. Okay, and okay, this is going to give me a typo later on. Okay, so yep, I think this is pretty much it. Okay, and if I just show you now by executing this code, okay, it says embedding is not defined. Yes, definitely we will be having this typo over here, and let's just execute it. Okay, yep, done. And if you see now the same shape, that is 128 768, so just quickly checking it, I will just add another sentence over here. Okay, I maybe hate this. Thank you for the suggestion. Okay, so this is going to be the I hate this, and now I will be taking these input IDs and I will call this with the two input sequence. Okay, so you can see now we have our embedding layer is flexible to work on any number of sequences. Okay, so this time we have two input sequences, each of 128 maximum size, and against each token in that 128 token size we have 768 dimensions. Okay, so this is how we can implement this embedding layer. Quickly just check it against the model. Okay, so I think if we just check the model like this, model dot module. Okay, and here it gives us this. Let me just from this I want to import the embeddings layer. Okay, and within this I also okay, first of all let me execute this. Yeah, let me now import inspect from Python, and this inspect has this method. We can use get source, and in this get source I am going to pass the embeddings dot init. Okay, and if I just simply print it, you can see this is the init of the embedding class in the transformer library. So these are the same. Over here we are just in the original model, they are registering a buffer. We are not registering any buffer. Okay, we are directly like passing these input IDs. So if we just look into the forward function of this, let's just call this forward now. So here you can see these are the optional, and we have this input IDs. Okay, and we are passing these input IDs, and what it basically is calculating, it is calculating the input IDs, the position embeddings. These position embeddings are basically, first of all, it's looks into if the position IDs is none, and inside this, so we are not passing these position IDs. Okay, so what we are doing, we are basically creating these position IDs. Okay, so these position IDs, you can see here, basically if in the buffer, so they are extracting it and creating the same kind of structure to match the input IDs, and if not, so they are making it the same way. If you look into this, okay, and then expanding it, okay, they are doing it with the input IDs. We are just first of all extracting the input IDs, these batch sizes and sequence length from the input IDs, and we are passing them separately to the expand. Okay, but of course, if we simply pass this input IDs, it will catch the shape of the input IDs. Okay, and then you can see the position embeddings, self.position embeddings, then they are adding them. We are doing the same, then layer norm, then dropout embeddings, and then this return embeddings. Okay, so if you look into the forward function, okay, we have the same forward function for this, and we are first of all extracting the input IDs from the lookup table. Then we are creating these position IDs for all of the sequences, each and every batch, and then we are expanding it along the batches. So finally then we can add them. Okay, and yep, this is how we get the embeddings, and then we just simply pass it through the layer normalization and the dropout. Okay, and okay, so this dropout is nothing but it is going to switch off some random values of this output. So it is basically forcing the model not to be dependent on some specific features. So with each time in the training loop, it will be applying this 10% on this output, and this is going to help us minimizing the overfitting. Okay, if I show you how it is performed, so let's say we have these 4 values in the output. Okay, so this, let's say we have 50%, 0.5, so it will randomly 50% of these outputs, and the remaining it will be multiplying it with 1 over 1 minus p, so the overall magnitude is not affected. Okay, so this is pretty much it about the layer embedding layer. Okay, we have in this specific video we have covered this embedding, and you can see we get this same kind of output shape, and this same shape we are going to pass it to the next layer, that is going to be the encoder part. Okay, so this is it for this video. I hope you enjoyed the lecture, and I see you in the next lecture. Till then, bye bye.